Drifting through the dark void between stars in our galaxy, there are more planets wandering alone in interstellar space than there are stars shining in the entire Milky Way, a hidden population of worlds so vast that it fundamentally changes our understanding of planetary formation, galactic structure, and the potential for life in the universe. These are rogue planets, worlds that have been ejected from their birth star systems and now travel through space as cosmic nomads, invisible to most of our detection methods, yet potentially numbering in the trillions throughout our galaxy alone. The discovery that rogue planets outnumber stars represents one of the most profound revelations in modern astronomy, because it suggests that the majority of planets in the universe exist in complete darkness, without the warmth and light of a parent star. While we've grown accustomed to thinking of planets as objects that orbit stars like the 8 planets in our solar system, the universe contains a hidden majority of worlds that have broken free from stellar gravitational bonds and now wander the galaxy independently. Recent observations using gravitational microlensing techniques have revealed that for every star in the Milky Way, there are likely 1.5 to 2 rogue planets drifting through interstellar space. With roughly 100 billion stars in our galaxy, this implies the existence of 150 to 200 billion rogue planets, a population of homeless worlds that vastly exceeds the number of bound planets orbiting stars in conventional planetary systems. Dr. Takahiro Sumi's groundbreaking research using the optical gravitational lensing experiment, OGLE, first provided statistical evidence for this enormous population of rogue planets by analyzing how these invisible worlds briefly magnify the light from background stars as they pass between Earth and distant stellar sources. These microlensing events last only hours to days, but they reveal the presence of dark objects with masses consistent with planets wandering freely through space. The implications of this discovery extend far beyond simple planetary counting. If rogue planets truly outnumber stars, it means that most planets in the universe exist under conditions completely unlike those in our solar system worlds, perpetually frozen in the darkness of interstellar space, with surface temperatures approaching absolute zero and no possibility of receiving stellar energy to drive atmospheric or geological processes. The formation mechanisms that create rogue planets involve some of the most violent and chaotic processes in planetary system evolution. Young star systems are dynamically unstable environments where gravitational interactions between forming planets can eject some worlds entirely from their birth systems, sending them on eternal journeys through interstellar space. Computer simulations suggest that these ejection events may be so common that they represent the normal outcome of planetary formation rather than rare catastrophic events. Dr. Sean Raymond's dynamical simulations of early planetary system evolution show that gravitational scattering between massive planets can easily provide enough energy to eject Earth mass or larger worlds from their star systems entirely. These simulations suggest that for every planet that ends up in a stable orbit around a star, one or more planets may be ejected into interstellar space during the chaotic early phases of system formation. The observational evidence for rogue planets comes primarily from gravitational microlensing surveys that can detect dark objects by their gravitational effects on light from background stars. Unlike conventional planet detection methods that rely on measuring stellar wobbles or transit signals, microlensing can detect isolated planets that have no parent star to influence observationally. Recent microlensing surveys, including OGLE, MOA, microlensing observations in astrophysics, and the upcoming Nancy Grace Rawlings Space Telescope mission have detected dozens of candidate rogue planet events and established statistical constraints on their galactic population. These observations suggest that Jupiter-mass rogue planets are particularly common, though Earth-mass rogues may exist in even greater numbers. The mass distribution of rogue planets appears to favor larger worlds, possibly because more massive planets are easier to detect. through microlensing or because they are more likely to survive the ejection process that removes them from their birth systems. However, theoretical models suggest that smaller rogue planets, including Earth-sized and sub-Earth-sized worlds, may actually be the most numerous members of the rogue planet population. Dr. Louis Strigari, a statistical analysis of microlensing data, indicates that the rogue planet population extends down to very low masses, potentially including objects as small as Mars or even the Moon. If confirmed, this would suggest that planetary system formation processes routinely eject not just large planets but also smaller planetary embryos and fully formed terrestrial worlds. The survival prospects for rogue planets in interstellar space depend critically on their internal heat sources and atmospheric properties. Worlds ejected from their star systems retain whatever internal radioactive heating they possessed at formation, while large planets may maintain substantial atmospheric pressure that could theoretically support subsurface liquid water oceans similar to those found on Jupiter's moon Europa. The potential for life on rogue planets represents one of the most intriguing implications of their vast numbers. While surface conditions on these worlds would be extremely hostile, subsurface environments heated by radioactive decay or tidal heating could theoretically maintain liquid water for billions of years, creating isolated biospheres that exist independently of stellar energy. If you are fascinated by the hidden structure of our galaxy and the possibility that most planets exist as cosmic wanderers, subscribe and hit the thumbs up button. And here's a mind-bending question. If rogue planets with subsurface oceans could potentially harbor life and they outnumber star-orbiting planets by at least 2 to 1, could the majority of life in the universe exist in permanent darkness on worlds we can barely detect? Comment your thoughts on this cosmic possibility below. The discovery that rogue planets outnumber stars challenges fundamental assumptions about planetary system architecture and suggests that our solar system is configuration with multiple planets in stable orbits around a central star may represent the minority outcome of planetary formation processes. Most worlds may instead exist as solitary travelers, shaped by completely different evolutionary processes than those that determine the characteristics of star-orbiting planets. The galactic implications of a vast rogue planet population include effects on galactic chemical evolution, stellar formation processes, and the overall mass budget of the Milky Way. Rogue planets contribute to the galaxy's dark matter inventory and participate in gravitational interactions that affect stellar orbits and galactic structure evolution over cosmic timescales. Future observations will dramatically expand our knowledge of rogue planet populations through space-based microlensing surveys, direct imaging of nearby rogue planets, and statistical analysis of their mass functions and spatial distributions. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the most comprehensive census of rogue planets ever attempted. Tonight, we're going to explore one of the most surprising discoveries in modern astronomy, the revelation that our galaxy contains a hidden population of wandering worlds that vastly outnumbers all the stars we can see, fundamentally changing our understanding of planetary formation, galactic structure, and the potential distribution of habitable environments throughout the universe. The journey ahead will take us through the violent processes that eject planets from their birth systems, the observational techniques that revealed this hidden population, the survival strategies that allow worlds to persist in the darkness of interstellar space, and the profound implications for our understanding of planetary systems and life in the universe. Consider this. Every time you look up at the night sky and see the stars of the Milky Way, there are likely twice as many invisible planets wandering in the darkness between those stars, a hidden majority of worlds that exist under conditions so alien that they challenge every assumption we've made about what planetary environments can look like and where life might be able to survive in our cosmos. Chapter 1. Invisible Worlds. The vast majority of planets in the Milky Way exist as invisible wanderers that emit no light of their own and reflect no starlight because they drift alone in the darkness of interstellar space, completely disconnected from any stellar system. These rogue planets represent the hidden backbone of galactic planetary populations, outnumbering both stars and star-orbiting planets while remaining almost entirely undetectable to conventional astronomical observation methods that rely on stellar interactions to reveal planetary presence. The invisibility of rogue planets stems from fundamental physics. Planets do not generate their own light through nuclear fusion like stars, and without a nearby star to illuminate them, they exist incomplete. Darkness except for the faint thermal radiation they emit due to their internal heat. At typical interstellar distances, even a Jupiter-sized rogue planet would appear dimmer than a candle viewed from thousands of miles away, making direct optical detection essentially impossible with current technology. Dr. David Bennett, his pioneering work on gravitational microlensing, has revealed that this invisible population may contain more worlds than all the stars in the galaxy combined. Microlensing events occur when a rogue planet passes between Earth and a background star, causing the planet's gravity to act as a natural magnifying lens that briefly brightens the distant star as light. These events provide the only practical method for detecting isolated planets in the dark reaches of interstellar space. The physics of gravitational lensing allows astronomers to detect objects that produce no observable light by measuring their gravitational effects on light from more distant sources. When a rogue planet passes in front of a background star, its gravitational field bends and focuses the starlight, creating a temporary brightening that can last from hours to days depending on the planet's mass and the geometry alignment. Recent statistical analysis of microlensing surveys by Dr. Przimek Mraz reveals that rogue planet detection events occur much more frequently than would be expected if such objects were rare. The frequency of these events suggests that unbound planets represent a major component of the galaxy's mass budget and may account for a significant fraction of the dark matter that affects galactic rotation curves. The mass range of detected rogue planets spans from superjupiters several times more massive than Jupiter down to objects with masses comparable to Earth or smaller. However, detection efficiency strongly favors more massive objects because their gravitational lensing effects are stronger and more easily detected, suggesting that the true population of rogue planets is likely dominated by smaller worlds that remain below current detection thresholds. Thermal emission from rogue planets provides another potential detection method, though one that requires extremely sensitive infrared observations. Large rogue planets retain significant internal heat from their formation and ongoing radioactive decay, causing them to emit infrared radiation that could theoretically be detected by space-based telescopes. However, the expected flux levels are so low that only the nearest rogue planets would be detectable through thermal emission. The Subaru telescope, as direct imaging surveys, have attempted to detect nearby rogue planets through their thermal emission, but have found only a handful of candidates, suggesting either that rogue planets are less common in the solar neighborhood or that most are too small and cold to emit detectable thermal radiation. These null results highlight the extreme observational challenges involved in studying the invisible planet population. Computer simulations of planetary system formation predict that rogue planet production should be a natural outcome of the dynamical evolution that occurs in young stellar systems. As protoplanets grow and migrate within circumstellar disks, gravitational interactions inevitably lead to close encounters that can provide some objects with sufficient energy to escape their birth systems entirely, becoming unbound wanderers in interstellar space. Dr. Hal Levison-Snice model simulations of early solar system evolution show that even our own solar system likely experienced dynamical instabilities that could have ejected additional planets during the first few 100 million years after formation. Evidence for such early ejection events might include the current orbital spacing of the giant planets, and the architectural features of the outer solar system. The survival mechanisms that allow rogue planets to maintain their integrity during and after ejection from stellar systems involve complex interactions between gravitational dynamics, atmospheric retention, and internal heat sources. Planets must survive the violent ejection process itself, retain substantial atmospheres despite the loss of stellar heating, and maintain internal heat sources sufficient to prevent complete atmospheric collapse. Atmospheric retention on rogue planets depends critically on planetary mass and composition because higher gravity helps retain atmospheric gases, while internal heat sources prevent atmospheric condensation and collapse. Large rogue planets with substantial hydrogen-helium atmospheres may maintain significant atmospheric pressures for billions of years, while smaller rocky planets face greater challenges in retaining their atmospheres in the extreme cold of interstellar space. The chemical evolution of rogue planet atmospheres differs dramatically from that of star-orbiting planets because photochemical processes driven by stellar ultraviolet radiation cease entirely once planets are ejected into interstellar space. Without stellar energy input, atmospheric chemistry becomes dominated by reactions driven by cosmic ray interactions, radioactive decay, and thermal processes powered by internal planetary heat. Dr. Dorian Abbott's atmospheric modeling studies suggest that thick hydrogen atmospheres can provide substantial greenhouse warming on rogue planets, potentially maintaining surface temperatures warm enough for liquid water even in the absence of stellar heating. These greenhouse effects could create habitable surface conditions on massive rogue planets with appropriate atmospheric compositions. The galactic distribution of rogue planets likely reflects the spatial distribution of star formation over cosmic history because planets are ejected from their birth systems during early dynamical evolution phases. Regions of the galaxy with higher stellar densities and more active star formation histories should contain correspondingly higher densities of rogue planets, creating spatial clustering patterns that mirror galactic structure. Observational biases strongly affect our current understanding of rogue planet populations because microlensing surveys preferentially detect planets along specific sightlines toward the galactic center where background star densities are highest. This geometric bias means that our current statistical constraints on rogue planet abundances may not be representative of their true galactic distribution. The age distribution of rogue planets depends on the timescales for planetary formation and ejection processes, with most rogue planets likely originating during the first few 100 million years of stellar system evolution when dynamical instabilities are most common. However, ongoing planetary scattering events in mature systems and stellar encounters in dense cluster environments can continue producing rogue planets throughout galactic history. Proper motion measurements of nearby stars occasionally reveal high-velocity objects that may represent rogue planets passing through the solar neighborhood. These astrometric detections provide complementary information to microlensing surveys but remain extremely challenging because rogue planets produce no optical signals and must be detected through their gravitational perturbations of nearby stars or their extremely faint thermal emission. The potential for multiple rogue planet systems, gravitationally bound pairs, or groups of ejected planets remains largely unexplored but could represent an important component of the invisible planet population. If planetary ejection events sometimes remove multiple objects from their birth systems while preserving gravitational binding between them, the resulting rogue planet systems would represent exotic planetary architectures that have no analogs among star-orbiting systems. Future space-based surveys will dramatically improve our ability to study invisible rogue planet populations through both microlensing and direct detection methods. The Nancy Grace Rawlings Space Telescope will conduct systematic microlensing surveys with unprecedented sensitivity to Earth mass and smaller rogue planets, while future infrared telescopes may achieve the sensitivity needed to detect thermal emission from nearby rogue planets. The implications of a vast invisible planet population extend beyond astronomy to astrobiology, galactic evolution, and our understanding of planetary system formation processes. If most planets exist as rogue wanderers rather than star-orbiting worlds, the conditions for life in the universe may be very different from those we observe in our solar system, with implications for the search for extraterrestrial life and the assessment of galactic habitability. As we prepare to explore the ejection mechanisms that create these invisible worlds, remember that the revelation of a hidden majority of planets fundamentally changes our perspective on planetary systems and suggests that the familiar architecture of star-orbiting worlds represents just a small fraction of the total planetary population in our galaxy, with profound implications for understanding cosmic evolution and the distribution of potentially habitable environments throughout the universe. Chapter 2. Ejection Mechanisms. The violent birth of rogue planets occurs through catastrophic ejection events that tear worlds away from their stellar systems and launch them into the darkness of interstellar space, involving gravitational interactions so extreme that they can accelerate planet-sized objects to velocities exceeding 30 kilometers per second, fast enough to escape the gravitational binding of their birth systems entirely. Understanding these ejection mechanisms reveals how planetary formation processes naturally create the vast population of wandering worlds that outnumber stars in the Milky Way. Gravitational scattering represents the primary mechanism for planet ejection, occurring when close encounters between massive planets exchange orbital energy in ways that can accelerate one planet beyond the escape velocity of its stellar system. These scattering events are inevitable consequences of planetary migration and orbital evolution in young systems where multiple massive planets interact gravitationally over millions of years. Dr. Frederick Rossio's numerical simulations of planetary system evolution demonstrate that systems containing multiple Jupiter-mass planets almost invariably experience violent dynamical instabilities that result in planet-planet scattering events. These simulations show that roughly 50% of such systems eject at least one planet, while the remaining planets settle into more stable but highly eccentric orbits that reflect their violent dynamical histories. The physics of gravitational scattering involves three-body interactions where two planets approach each other closely, while both orbit a central star, creating a gravitational slingshot effect that can dramatically alter both planets' orbital energies. The planet that gains energy may acquire enough velocity to escape the system entirely, while the planet that loses energy typically falls into a closer, more eccentric orbit around the central star. Planet-planet scattering efficiency depends critically on the mass ratio between interacting planets and their initial orbital configurations. Dr. Eric Ford's analytical studies show that equal mass planets maximize scattering cross-sections and ejection probabilities, while systems with one dominant massive planet tend to preserve the massive world while ejecting smaller companions that cannot compete gravitationally. Stellar flyby events represent another important ejection mechanism, particularly in dense stellar clusters, where close encounters between stars can disrupt planetary systems through external gravitational perturbations. When a passing star approaches within a few hundred astronomical units of a planetary system, its gravitational influence can destabilize planetary orbits and eject outer planets from their host systems. Dr. Barbara MacArthur's studies of planetary systems and stellar clusters reveal that close stellar encounters occur frequently enough in dense environments to represent a major source of rogue planet production. These encounters preferentially eject outer planets while leaving interplanetary systems relatively unperturbed, creating a bias toward more massive rogue planets that originally formed in the outer regions of their birth systems. The timescales for planetary ejection vary dramatically depending on the specific mechanisms involved and the initial conditions in planetary systems. Rapid ejection events driven by direct planet-planet scattering can occur within a few orbital periods, potentially within thousands of years, while slower processes involving secular perturbations and orbital migration can operate over millions of years before triggering instabilities. Binary star dynamics create additional pathways for planet ejection through complex gravitational interactions, involving planetary orbits around one or both components of stellar binaries. The Kozyolov mechanism, which causes periodic oscillations in orbital eccentricity and inclination, can drive planets into highly eccentric orbits that become unstable and lead to ejection or collision with the central stars. Dr. Smatter-Naos' research on planetary dynamics in binary star systems shows that planets orbiting the secondary star and wide binary systems are particularly susceptible to ejection through Kozyolov cycles that can pump orbital eccentricities to extreme values. These mechanisms may explain the observed deficit of planets around secondary stars in wide binary systems compared to single star systems. This driven migration during the early phases of planetary system formation can also lead to ejection events when massive planets migrate inward through gravitational interactions with circumstellar disks. If migration brings massive planets too close together, subsequent dynamical instabilities can eject some planets while others continue migrating or settle into resonant configurations. The Grand-Tag model of early solar system evolution, developed by Dr. Kevin Walsh, proposes that Jupiter underwent extensive inward and outward migration that could have ejected an early generation of super-Earth planets from the inner solar system. This scenario suggests that even our solar system may have experienced planet ejection events during its early dynamical evolution. Mass-dependent ejection probabilities reflect the physics of gravitational scattering processes, with different planet masses showing different susceptibilities to ejection depending on their gravitational binding energies and scattering cross-sections. Low-mass planets are more easily ejected because they have lower gravitational binding energies, while very high-mass planets can dominate dynamical interactions and eject their smaller companions. Computer simulations by Dr. Sean Raymond indicate that Earth-mass planets are ejected roughly twice as frequently as Jupiter-mass planets during dynamical instabilities, suggesting that the rogue planet population should be dominated by terrestrial mass objects rather than gas giants. However, observational selection effects favor detection of more massive rogue planets, creating apparent contradictions between theoretical predictions and observational constraints. Planetary embryo ejection during the late stages of terrestrial planet formation represents another pathway for creating smaller rogue planets, as gravitational interactions between growing protoplanets can eject some objects before they reach full planetary sizes. These ejected embryos would represent a population of sub-Earth mass rogue objects that could significantly outnumber larger rogue planets. The NICE model of outer solar system evolution demonstrates that even relatively late-stage dynamical instabilities occurring hundreds of millions of years after initial system formation can still produce planet ejection events. This model suggests that the late heavy bombardment resulted from a delayed dynamical instability that could have ejected additional ice giant planets from the outer solar system. Tidal disruption of planetary systems by central stellar evolution can also lead to planet ejection when stellar mass loss reduces the gravitational binding of planetary orbits, or when stellar expansion during red giant phases engulfs and ejects inner planets through tidal interactions. These mechanisms become important for understanding rogue planet production around evolved stellar systems. Dr. Dmitry Veer's studies of planetary system evolution around white dwarf stars show that post-main sequence stellar mass loss can destabilize planetary systems and eject surviving planets into interstellar space. These processes suggest that stellar death represents an additional source of rogue planet production that operates over longer timescales than early dynamical ejection events. Supernova explosions in binary systems containing planetary companions can eject planets through asymmetric explosions that impart kick velocities to stellar remnants and any surviving planetary systems. While relatively rare, these violent events can accelerate planets to extremely high velocities and create hypervelocity rogue planets with unusual kinematic properties that capture ejection balance in dense stellar environments like globular clusters creates complex dynamics where planets can be both ejected from their birth systems and subsequently captured by other stars, creating temporary planetary systems that may experience multiple ejection and capture cycles over cosmic timescales. These processes blur the distinction between rogue planets and conventional planetary system members. Multi-planet ejection events can occur when single dynamical instabilities remove multiple planets from stellar systems, simultaneously creating populations of rogue planets that originated from the same system and may retain similar chemical compositions and formation signatures despite their current isolation in interstellar space. Statistical analysis of ejection mechanisms suggests that planet-planet scattering dominates rogue planet production for massive objects, while stellar encounters and binary dynamics become increasingly important in dense stellar environments and multiple star systems. The relative importance of different mechanisms varies with galactic environment and stellar population characteristics. Future theoretical developments in understanding ejection mechanisms focus on incorporating more realistic physics, including general relativity effects, stellar evolution, disk-planet interactions, and multi-body dynamics to better predict rogue planet production rates and properties. These improved models will help interpret observations from next-generation surveys and provide better constraints on galactic rogue planet populations. As we prepare to explore the gravitational chaos that drives these ejection events, remember that the mechanisms creating rogue planets are not rare catastrophic accidents, but natural consequences of planetary system formation and evolution, suggesting that the production of wandering worlds represents a fundamental aspect of how planetary systems develop and evolve throughout cosmic history. Chapter 3. Gravitational Chaos. The dynamical evolution of young planetary systems unfolds as a cosmic dance of gravitational chaos, where the slightest perturbations can cascade into system-wide instabilities that reshape planetary architectures and eject entire worlds into interstellar space. This gravitational chaos represents one of the most fundamental aspects of planetary system formation, involving complex many-body interactions that make long-term orbital evolution inherently unpredictable and ensure that planet ejection events are inevitable consequences rather than rare accidents in the formation of planetary systems. Unbody gravitational dynamics governs the complex interactions between multiple planets orbiting a central star, creating a mathematical system so complex that long-term predictions become impossible due to sensitive dependence on initial conditions, the hallmark of chaotic dynamics. Even tiny uncertainties in planetary masses, positions, or velocities can grow exponentially over time, leading to completely different evolutionary outcomes for nearly identical initial configurations. Dr. Jacques Lasker, as groundbreaking studies of solar system dynamics revealed that even our own planetary system exhibits chaotic behavior, with Mercury's orbit showing potential for dramatic changes or even ejection over timescales of billions of years. These calculations demonstrate that gravitational chaos operates even in apparently stable systems and can lead to major architectural changes over cosmic timescales. The three-body problem represents the simplest case where gravitational chaos becomes manifest, involving interactions between two planets orbiting a central star. While the two-body problem of a single planet orbiting a star has well-defined solutions, adding even one additional planet creates a system where exact analytical solutions become impossible, and numerical simulations reveal complex chaotic dynamics. Hill-sphere interactions occur when planets approach each other closely enough that their mutual gravitational attraction begins to dominate over their attraction to the central star. These close encounters can exchange orbital energy and angular momentum between planets, leading to dramatic changes in orbital elements and potentially providing sufficient energy for planetary ejection from the system. Dr. Jack Wisdom's research on chaotic planetary dynamics shows that Hill-sphere crossing events represent phase transitions in planetary system evolution, where small changes in approach parameters can lead to dramatically different outcomes, including orbital exchange, collision, or ejection. These events cannot be predicted deterministically due to their extreme sensitivity to initial conditions. Resonance overlap creates regions of phase space where multiple gravitational resonances interact, creating webs of chaotic dynamics that can trap planets in unstable orbital configurations. When planets become trapped in overlapping resonances, their orbital evolution becomes chaotic and can lead to large changes in orbital elements over relatively short timescales. The Kirkwood gaps in the asteroid belt demonstrate how resonance overlap with Jupiter creates chaotic regions where stable orbits cannot exist, clearing specific orbital distances of small bodies through repeated close encounters and ejection events. Similar mechanisms operate in planetary systems where multiple massive planets create complex resonance structures. Secular chaos arises from long-term gravitational interactions that slowly change planetary orbital elements over millions of years without involving close encounters between planets. This type of chaos can cause planetary orbits to become increasingly eccentric until they cross the orbits of other planets, triggering violent instabilities that can lead to ejection events. Dr. Konstantin Batygин's analytical studies of secular dynamics show that systems with multiple planets on initially circular orbits can develop large eccentricities through secular chaotic evolution, creating delayed instabilities that occur long after initial system formation. These mechanisms explain how apparently stable planetary systems can suddenly become unstable and eject planets. Mean motion resonances create periodic gravitational interactions between planets that can either stabilize or destabilize orbital configurations depending on the specific resonance and the presence of additional perturbations. Low-order resonances like 2-to-1 or 3-to-2 can provide stability, while high-order resonances and near-resonant configurations often lead to chaotic behavior. The Kozai-Lidov mechanism represents a specific type of secular chaos that occurs in hierarchical systems, where a distant perturber causes periodic oscillations in the eccentricity and inclination of inner orbits. These oscillations can drive orbital eccentricities to extreme values, leading to close approaches to central stars or ejection from the system entirely. Planetary migration driven by displanet interactions can trigger gravitational chaos when migrating planets encounter each other in resonant configurations or when migration brings planets into unstable orbital configurations. The combination of dissipative forces from circumstellar disks and conservative gravitational interactions creates complex dynamics that frequently lead to instabilities. Dr. Kristen Menu's studies of migration-induced instabilities show that convergent migration, where multiple planets migrate inward toward the central star, almost inevitably leads to gravitational chaos and planet ejection events. These mechanisms may explain why close-in planetary systems often contain fewer planets than expected from formation models. Stochastic forcing from turbulent circumstellar disks adds random perturbations to planetary orbits during the early phases of system evolution, introducing additional sources of chaos that can trigger instabilities even in configurations that would be stable in the absence of disk perturbations. These random forces make planetary system evolution even more unpredictable. Lyapunov exponents provide quantitative measures of chaotic behavior in planetary systems by characterizing how rapidly nearby trajectories diverge in phase space. Systems with positive Lyapunov exponents exhibit chaotic dynamics where small uncertainties grow exponentially, making long-term predictions impossible and ensuring that statistical rather than deterministic approaches are needed. Phase-space structure in planetary systems reveals the underlying organization of chaotic dynamics through surfaces of section and Poincare maps that show how orbital evolution is organized around stable and unstable periodic orbits. Understanding this structure helps identify regions of phase space that are particularly prone to ejection events. Arnold diffusion represents a mechanism for slow, chaotic transport in planetary systems where orbits can wander through phase space along weakly chaotic layers, gradually changing orbital elements until they reach regions where rapid instabilities can occur. This mechanism provides pathways for delayed ejection events that occur long after initial system formation. Machine learning approaches are being developed to predict planetary system stability and ejection probabilities using artificial neural networks trained on large databases of numerical simulations. Dr. Daniel Tamayo's machine learning models can predict system stability over billions of years based on initial orbital configurations, providing new tools for understanding gravitational chaos. Symplectic integration methods preserve the underlying geometric structure of Hamiltonian dynamics in planetary systems, allowing accurate long-term numerical simulations that reveal chaotic behavior without artificial numerical diffusion. These methods are essential for studying gravitational chaos over the long timescales relevant for planetary system evolution. The Kolmogorov-Arnold-Moser theorem describes how small perturbations can destroy stable periodic orbits in gravitational systems, creating chaotic regions where regular motion becomes impossible. This mathematical framework provides fundamental insight into why planetary systems are inherently unstable and prone to ejection events. Statistical mechanics approaches to planetary dynamics treat ejection events as irreversible transitions in phase space, similar to chemical reactions or phase transitions in thermodynamic systems. These approaches provide ensemble average descriptions of ejection rates and final state distributions without requiring detailed knowledge of individual system evolution. Gravitational waves from planetary systems undergoing chaotic evolution could potentially carry signatures of ejection events and orbital instabilities, though the expected signal amplitudes are far below current detection thresholds. Future gravitational wave observatories might be able to detect these signals from nearby planetary systems. The butterfly effect in planetary dynamics means that tiny changes, such as the influence of a passing asteroid or small measurement errors in initial conditions, can completely change the long-term evolution of planetary systems. This extreme sensitivity makes individual system evolution unpredictable, while statistical properties remain well-defined. Escape dynamics in chaotic planetary systems follow power law, scaling relationships that relate ejection timescales to initial orbital separations and planetary masses. These scaling laws provide insights into the underlying physics of ejection events and help predict statistical properties of rogue planet populations. Future developments in understanding gravitational chaos include improved numerical methods, machine learning applications, and theoretical advances in nonlinear dynamics that will provide better frameworks for predicting and understanding the complex evolutionary pathways that lead from planetary formation to the creation of vast populations of rogue planets wandering through interstellar space. As we prepare to explore the detection challenges involved in finding these ejected worlds, remember that gravitational chaos is not a flaw in planetary system formation, but a fundamental feature that ensures most planetary systems will experience dramatic evolutionary changes, creating the hidden majority of planets that wander alone through the galaxy as evidence of the inherently unstable nature of gravitational dynamics in multi-planet systems. Chapter 4. Detection Challenges: Discovering planets that emit no light of their own and wander alone through the vast darkness of interstellar space represents one of the most extreme observational challenges in astronomy, requiring innovative detection techniques that can reveal invisible objects through their subtle gravitational effects on background light sources or their faint thermal emissions. The detection of rogue planets pushes observational astronomy to its limits and demands creative approaches that differ fundamentally from conventional planet hunting methods that rely on measurable interactions between planets and their host stars. Gravitational microlensing provides the primary detection method for rogue planets, exploiting Einstein's general theory of relativity to reveal dark objects through their gravitational effects on light from distant background stars. When a rogue planet passes between Earth and a background star, the planet's gravitational field acts as a natural lens that bends and focuses the starlight, creating a temporary brightening event that can last from hours to days. Dr. Andy Gould is pioneering microlensing techniques have revealed that successful rogue planet detection requires monitoring millions of background stars continuously to catch the rare alignment events that produce detectable lensing signals. The probability of any individual star being lensed by a rogue planet is extremely small, roughly 1 in a million per year, making statistical analysis of large samples essential for constraining rogue planet populations. The duration and shape of microlensing light curves provide diagnostic information about the mass and distance of lensing objects, allowing astronomers to distinguish planetary mass lenses from stellar mass lenses and to estimate physical properties of detected rogue planets. Shorter duration events typically indicate lower mass objects or more distant lenses, while longer events suggest more massive objects or closer proximity. Observational selection effects strongly bias microlensing surveys toward detecting more massive rogue planets, because higher mass objects create stronger gravitational lensing effects and longer duration events that are easier to detect and characterize. This bias means that current observations preferentially reveal Jupiter mass and super-Jupiter mass rogue planets while remaining relatively insensitive to Earth mass and smaller rogue worlds. Dr. Przymek Ma's statistical analysis of OGLE microlensing data reveals that correcting for these selection effects suggests the existence of a much larger population of lower mass rogue planets that remain below current detection thresholds. The implied abundance of Earth mass rogue planets could exceed that of more massive rogue planets by factors of 10 or more. Degeneracies in microlensing observations create ambiguities in determining the physical properties of detected rogue planets because multiple combinations of mass, distance, and proper motion can produce similar lensing light curves. Breaking these degeneracies requires additional observations such as parallax measurements or detection of higher-order lensing effects. Space-based microlensing observations offer significant advantages over ground-based surveys by avoiding atmospheric effects, achieving better photometric precision, and enabling simultaneous observations from multiple vantage points that can break parameter degeneracies. The Nancy Grace Roman Space Telescope will conduct the most comprehensive rogue planet survey ever attempted. Direct imaging detection of rogue planets through their thermal emission represents an alternative approach that could reveal nearby rogue planets through extremely sensitive infrared observations. Young, massive rogue planets retain substantial internal heat from formation and radioactive decay, causing them to emit detectable thermal radiation in the near-infrared spectral region. The Subaru telescope, as direct imaging surveys, have searched for nearby rogue planets, but have found only a handful of candidates, highlighting the extreme observational challenges involved in detecting thermal emission from isolated planetary mass objects. These null results suggest that most rogue planets are either too distant, too old, or too small to emit detectable thermal radiation. Astrometric detection methods could potentially reveal nearby rogue planets through their gravitational perturbations of stellar motions, though the required precision exceeds current observational capabilities by several orders of magnitude. Future space-based astrometry missions might achieve the precision needed to detect nearby rogue planets through their gravitational influence on stellar positions. Proper motion surveys occasionally identify high-velocity objects that could represent nearby rogue planets moving through the local stellar neighborhood. However, distinguishing planetary mass objects from low-mass brown dwarfs requires spectroscopic follow-up observations that are extremely challenging for such faint targets. Wide-field survey telescopes like the Vera Rubin Observatory will dramatically improve the discovery rate of directly imaged rogue planet candidates through systematic monitoring of large sky areas, though distinguishing true rogue planets from background stars and galaxies will require careful photometric and astrometric analysis. Occultation events could potentially reveal rogue planets when they pass in front of background stars and temporarily block stellar light, creating brief dimming events that could be detected by high-cadence photometric surveys. However, these events would be extremely brief and rare, making them extremely difficult to detect and confirm. Radio emission detection represents a speculative approach for finding rogue planets with active magnetospheres that could generate detectable radio signals through interactions with cosmic rays or magnetic field dynamics. However, no confirmed radio detections of rogue planets have been reported, suggesting that such emissions are either very weak or non-existent. Atmospheric signatures could potentially reveal rogue planets with substantial atmospheres through spectroscopic detection of molecular absorption features, though this would require extremely sensitive observations of very faint thermal emission sources. Future extremely large telescopes might achieve the sensitivity needed for atmospheric characterization of nearby rogue planets. Machine learning techniques are being developed to improve the efficiency of rogue planet detection by automatically identifying microlensing events in large photometric datasets and distinguishing planetary lensing signatures from stellar variability and instrumental effects. These automated approaches will become essential for processing data from future large-scale surveys. Follow-up observations of microlensing events require rapid response capabilities because lensing events are transient phenomena that cannot be repeated or observed at later times. Coordinated networks of telescopes around the globe provide continuous monitoring capabilities that can capture complete lensing light curves and enable detailed characterization of detected events. Systematic uncertainties in rogue planet detection include photometric calibration errors, contamination by stellar variability, and instrumental effects that can mimic or obscure genuine microlensing signals. Careful analysis protocols and statistical techniques are required to minimize these uncertainties and ensure reliable detection and characterization of rogue planet candidates. Population synthesis models that combine theoretical predictions for rogue planet formation with observational selection effects provide frameworks for interpreting detection statistics and constraining the true abundance and mass distribution of galactic rogue planet populations. These models must account for complex biases in current observations. False positive identification represents a significant challenge in rogue planet detection because other astrophysical phenomena can produce signals that mimic planetary microlensing events. Binary star systems, stellar variability, and instrumental artifacts can all create false signals that require careful analysis to identify and exclude. Future technological developments, including improved detector sensitivity, space-based platforms, and novel observation techniques will dramatically enhance our ability to detect and characterize rogue planet populations. The James Webb Space Telescope may be able to detect thermal emission from nearby young rogue planets, while future gravitational wave detectors might reveal rogue planets through their effects on pulsar timing. Statistical analysis methods for extracting rogue planet population properties from limited observational datasets require sophisticated techniques that can account for selection effects, observational biases, and systematic uncertainties while providing robust constraints on the abundance and properties of different rogue planet populations. The detection rate predictions for future surveys suggest that next-generation facilities will discover thousands of rogue planet candidates, providing statistical samples large enough to characterize population properties and test theoretical predictions for rogue planet formation and evolution. These discoveries will transform our understanding of planetary system architecture and galactic structure. International collaboration in rogue planet detection involves coordinated survey programs, data sharing protocols, and standardized analysis techniques that maximize the scientific return from observational investments, while ensuring that discoveries can be confirmed and characterized through independent observations. As we prepare to explore the population statistics that these challenging observations are beginning to reveal, remember that the detection of rogue planets represents one of astronomy's greatest technical achievements, requiring innovative observational techniques and sophisticated analysis methods to reveal a hidden majority of worlds that exists in the darkness between stars, fundamentally changing our understanding of planetary populations throughout the galaxy. Chapter 5. Population Statistics. The statistical analysis of rogue planet observations reveals a hidden galactic population that may contain between 150 billion and 200 billion wandering worlds, a number so staggering that it fundamentally reshapes our understanding of planetary system formation and suggests that the majority of planets in the universe exist as cosmic nomads rather than as members of conventional stellar systems. These population statistics emerge from careful analysis of microlensing, surveys that must account for complex observational biases, and detection efficiencies to extract meaningful constraints on the true abundance of rogue planets throughout the Milky Way. Microlensing event rates provide the primary observational constraint on rogue planet populations, with surveys like OGLE optical gravitational lensing experiment and MOA microlensing observations in astrophysics, detecting dozens of candidate rogue planet events over the past 2 decades. Dr. Takahiro Sumi's analysis of MAOA survey data first established that Jupiter-mass rogue planets occur with a frequency of approximately 1.5 per main sequence star, suggesting a vast population of massive rogue worlds. The mass function of rogue planets, the distribution of planet masses within the rogue population, shows evidence for increasing abundance toward lower masses, similar to the mass functions observed for bound planets in conventional planetary systems. However, observational selection effects strongly favor detection of more massive rogue planets, making it extremely difficult to constrain the abundance of Earth mass and smaller rogue worlds. Dr. Przemek's comprehensive analysis of OGLE data reveals that when corrected for detection, biases the implied abundance of Earth mass. Rogue planets could be several times higher than that of Jupiter-mass rogues, suggesting that terrestrial mass wanderers represent the dominant component of the galactic rogue planet population. This finding has profound implications for understanding planetary formation processes and galactic structure. Statistical extrapolation from detected samples to total galactic populations requires sophisticated modeling that accounts for the spatial distribution of microlensing surveys, the geometry of lensing events, and the detection efficiency as a function of planet mass and distance. These models suggest that the total number of rogue planets in the Milky Way exceeds the number of stars by factors of 1.5 to 2. The spatial distribution of rogue planets likely follows the distribution of stellar populations throughout the galaxy because rogue planets originate from stellar systems and are ejected during early dynamical evolution phases. This suggests higher concentrations of rogue planets in the galactic disk and spiral arms where star formation has been most active over cosmic history. Galactic chemical gradients could affect rogue planet populations because planets forming at different galactocentric distances have different heavy element abundances that affect formation processes and final planet masses. Dr. Caitlin Casey's studies of galactic chemical evolution suggest that rogue planet properties might vary systematically with location within the galaxy. Age distributions of rogue planet populations depend on the timescales for planetary formation and ejection processes, with most rogue planets likely originating during the first few hundred million years after stellar system formation, when dynamical instabilities are most common. However, ongoing ejection processes in mature systems and stellar encounters can continue producing rogue planets throughout galactic history. Metallicity effects on rogue planet formation rates arise because higher heavy element abundances enable formation of more massive planets that are more likely to participate in gravitational scattering events leading to ejection. This suggests that rogue planet abundances might correlate with stellar metallicity and vary with galactic environment and stellar population characteristics. Kinematic properties of rogue planet populations reflect their origins in stellar systems and subsequent dynamical evolution during and after ejection events. Rogue planets should inherit velocity distributions similar to their parent stellar populations, while gaining additional velocity components from ejection processes that can reach tens of kilometers per second. Dr. Matthew Penny's kinematic modeling suggests that rogue planet velocity distributions should show signatures of their stellar origins while also exhibiting high-velocity tails produced by violent ejection events. These velocity distributions affect microlensing detection rates and could provide diagnostics for understanding ejection mechanisms and rogue planet origins. Comparative statistics between different galactic environments reveal that dense stellar regions like globular clusters and the galactic center might show enhanced rogue planet production rates due to increased rates of stellar encounters that can trigger planetary system instabilities. However, these same environments might also experience enhanced loss rates due to gravitational interactions with massive objects. The period-mass relationship for detected rogue planets shows systematic trends where more massive objects tend to produce longer-duration microlensing events, though this relationship is complicated by distance effects and proper motion variations. Understanding these systematic trends is essential for interpreting detection statistics and constraining population properties. Binary rogue planet systems represent a potentially important but poorly constrained component of the rogue planet population. If planetary ejection events sometimes remove multiple objects while preserving gravitational binding between them, the resulting binary or multiple rogue planet systems could significantly affect population statistics and detection rates. Dr. Yuki Yamamoto's theoretical studies suggest that binary rogue planet formation rates depend critically on the dynamics of multi-planet ejection events and the relative masses of ejected objects. Close binary rogue planet systems might be preferentially detected through their enhanced microlensing cross-sections compared to single rogue planets. Luminosity function modeling for directly detectable rogue planets involves understanding the relationship between planet mass, age, and thermal emission to predict how many rogue planets might be discovered through direct imaging surveys. Current models suggest that only the most massive, youngest, and nearest rogue planets would be detectable through thermal emission. Detection completeness corrections account for the fact that microlensing surveys detect only a small fraction of rogue planets due to geometric selection effects, finite survey duration, and detection thresholds. These corrections are essential for converting observed event rates to true space densities and total population estimates. Bayesian statistical analysis provides robust frameworks for combining observations from multiple surveys with different selection effects and detection efficiencies to constrain rogue planet population properties while properly accounting for statistical and systematic uncertainties. These methods are essential for extracting reliable population parameters from limited observational data. Mock survey simulations based on theoretical models of rogue planet populations provide crucial tests of statistical analysis methods and help quantify the reliability of population estimates derived from real observations. These simulations reveal potential biases in current estimates and guide the design of future surveys. Cross-correlation studies between rogue planet detections and stellar populations could reveal environmental effects on rogue planet formation and provide tests of formation models that predict specific relationships between stellar properties and planetary ejection rates. However, such studies require much larger statistical samples than currently available. Machine learning applications to population statistics include automated classification of microlensing events, regression analysis of population parameters, and anomaly detection techniques that could reveal rare or unusual rogue planet populations. These approaches become increasingly important as survey data volumes continue to grow. Future survey projections based on planned facilities like the Nancy Grace Roman Space Telescope suggest that rogue planet detection rates will increase by orders of magnitude, providing statistical samples large enough to characterize population properties in detail and test theoretical predictions for rogue planet formation and evolution. Systematic error analysis reveals that current population estimates remain uncertain by factors of several due to limited sample sizes, model uncertainties, and potential biases in detection and analysis procedures. Future observations will need to address these systematic limitations to provide more reliable population constraints. Population synthesis models that combine theoretical predictions for planetary formation and ejection with observational constraints provide frameworks for understanding how rogue planet populations relate to bound planetary populations and stellar system architectures throughout the galaxy. The implications of rogue planet population statistics extend beyond astronomy to astrobiology, galactic dynamics, and our understanding of planetary system formation processes. If rogue planets truly outnumber stars, they represent a major component of galactic mass and potentially provide vast numbers of environments where alternative forms of life might exist. Comparative planetology applications of population statistics include understanding how rogue planet properties relate to those of bound planets and whether ejection processes select for specific planet types or preserve representative samples of planetary populations formed around different types of stars. As we prepare to explore the formation pathways that create these vast populations of wandering worlds, remember that population statistics reveal rogue planets to be not rare curiosities, but fundamental components of galactic structure that outnumber stars themselves, requiring us to completely revise our understanding of planetary system, architecture, and the distribution of worlds throughout the universe.